We will continue with the disturbance and robustness in MPC. Every system will be affected by disturbances. So we need to tackle how we are going to see how in MPC the disturbance is handled. So our target is the robustness to model uncertainty. How we can handle the model uncertainty. So let us consider the constant disturbance case where we know a lower bound and upper bound for the disturbance. Now the system representation becomes like this, where dk is the constant disturbance. Now the model uncertainty may be due to different reasons. The first one is the incomplete knowledge of the plant model. Second one is the random process in the system dynamics and use of observer-based state estimates in the prediction model. So sometimes we may not be able to get the actual state measurement. So we will use an observer to predict the state estimate value. So that may cause error, or the system dynamics, sometimes we may use a linear dynamics. So incomplete knowledge of the plant model and random processes in the system dynamics and observer. All these might cause the disturbance. So all these will be taken care by this dk. One of the primary way by which MPC handles disturbance is by incorporating an integral action. So the benefits are, while we are handling the tracking control problem, we will be able to reach the set point accurately by using the integral action. And this method can also be used to tackle constant disturbances effectively. So the disturbance will be added as time goes, and corresponding action will be taken by the integrator so that the error is nullified. So now how we are incorporating integrator in the MPC. So we define argumentative state Z with planned X and integrator state V. So the new state will be Z k given k is equal to X k given k and V k given k. We will define what V is. V is a integrator state, and this integrator state V k plus 1 is equal to V k plus Y k. So now our argumented system will be Z in terms of Z, in terms of Z. Z k plus I plus 1 given k is equal to A 0 C I x k plus I given k, v k plus I given k. This is nothing but z k plus I given k, b 0 u k plus I given k. And our optimal feedback control will be u star k given k is equal to k s k plus k I v k, where k I v k, this is the contribution of the integrator. This is the integral gain. So this is how the feedback control will have a component which is contributed by the integrator. So that is how the MPC will be handling constant disturbances. It will incorporate integrator in the system and then take a corresponding action so that it nullifies the effect of the disturbance. In another technique by which we will handle disturbance is by robust constraint satisfaction. So to ensure feasibility at k plus first instant, we need to ensure that the predictions satisfy constraints for all possible disturbances. So at the kth instant, we have a measurement, and at the k plus first instant, we have a measurement which is disturbed. So while taking the control action, we need to account for the maximum possible disturbance. And the constraints also should be such a way that we need to ensure that for all possible disturbances, the states are feasible. So that will give a solution that will ensure the feasibility of the optimization problem at k plus first instant. So our states will be now divided into two parts. First is a nominal value, wherein we account for the predictions for d is equal to 0, and E k plus I given k accounts for disturbance effect. So the cases where D is not equal to 0. So z cap k plus I given k is equal to A0 C I raised to I zk plus phi I uk, and ek plus I given k is given by this term. So that accounts for the disturbance. This is for the nominal system. We have earlier seen what phi I is. So that is a matrix which consists of all the using B's and A's we have seen in the first lecture. So robust constraint satisfaction is nothing but U has an upper bound and lower bound, and the control sequence that we are finding will satisfy this control constraints. Whereas in state constraints, we have a lower bound of the state, we have an upper bound on the state, and that our predicted state and along with the error due to disturbance should satisfy this state constraint. So we are replacing the above constraint with the worst case values, nothing but the minimum of the value in the lower half and the maximum of this value in the upper half. So we will replace the worst case values here. So instead of this, we will use worst case values, the minimum value and the maximum value of the disturbance. So thereby, and this worst case values can be written in terms of tightening the constraint, like x lower bound is tightened by so much factor, this factor, and x upper bound is tightened by so much factor. So our nominal state should lie within the tightened state. So actual limit will be, say for example, minus 10 to 10, but the tightened limit will be lesser than that, say minus 8 and 8. So our tightened constraint is due to the disturbance. So we will consider the maximum value of disturbance and we tighten the constraint. So this is a concept that they are using in tube-based MPC. Now we will look into, so the above two methods are used to tackle the how MPC handles disturbances. So robust constraint satisfaction is one way, and by incorporating an integral action is the other way. There are different techniques by which there are special MPCs which are designed especially to handle disturbances. So mostly robust MPCs handle disturbances. Now we will see few other types of MPCs wherein we when we use a nonlinear model for say state predictions, we call them as a nonlinear model predictive control. We have an optimization problem. All the other things remains same as linear MPC. We have an objective function, and that objective function is minimized with respect to some constraints, state and control constraints, and we are finding a control sequence such that we minimize this objective function. In a stochastic MPC, we consider the disturbance, but the difference is that the difference with the robust MPC is that in robust case we take into account the maximum value of disturbance, and the bounds for the disturbance are known. But here we know the distribution of the disturbance, maybe a normal distribution, or the distribution of the system is known in stochastic MPC. So that information we are taking into account while designing the control in case of stochastic MPC, not the minimum and maximum bound. So here the object optimization problem is the same. We find a control sequence which minimizes the objective function. But here the objective function is expected value. Since we know the distribution of the disturbance, we can find the expected value of this cost function. So that is being minimized, subjected to the state constraints and control constraints. So that is how they design a stochastic MPC. So this is not as conservative as robust MPC. In robust MPC, we consider the maximum value of disturbance, hence the control required will be more. Whereas in stochastic MPC, we are using the distributional information of the disturbance in order to find a control sequence. So most of the things that I took in this lecture are taken from this book, wherein they describe about classical MPC, robust MPC, and stochastic MPC. And the book, which is written by Borelli, Bimparad, and Marari. So these are the other references. So what we have seen is the stability concept of model predictive control, how MPC handles the disturbances, how robustness is incorporated in MPC, then integral action in MPC, nonlinear model predictive control, and stochastic model predictive control. Thank you.